Today we'll be talking about a homogeneous nth order linear differential equation with constant coefficients. Now why is this special? Right? A(n) y to the nth order derivative plus a(m) minus 1 y m minus 1 plus da 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 plus a1 y prime plus a0 of y. Right? When this thing is equals to 0, so this is called a homogeneous. This is homogeneous, right? And this is called an nth order linear DE with constant coefficients. Now, the reason why we're studying constant coefficients is because generally when you have a linear like a linear or nth order differential equation with functions as coefficients, so imagine all of the a's just become functions of x here, then generally it's really hard and even sometimes impossible, and most of the time impossible, to solve these questions, except for specific cases which we will study later. So if it is equals to a function in terms of x, then it is called non-homogeneous. Non-homogeneous, right? So we're going to study a homogeneous equation, right? Now for a homogeneous equation, plus a(n) minus 1 n minus 1 plus da 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 plus a 0 y prime equals 0. We're going to study a specific type, and we're going to study the roots and the characteristic equation of this. Now, what are those things? Now, the roots, we're going to guess that there's a solution that will be e raised to the mth power of x. Let's assume that there is, right? So, a(n) becomes over here. Now, hold on. Yeah, so we're basically guessing or setting or making a smart guess that one of the types of solutions that there will be, right, is an exponential function, because that makes sense, right? So now imagine that we take the nth derivative of this. You would get m raised to the nth power e to the mx, right? Plus similarly a(n) minus 1 m n minus 1 e mx plus da 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 plus, let's say, a1 divided by mx plus a0 e to the mx. Right here it should be e to the mx, right? And that we're studying a homogeneous in this case, so we can factor out the emx and it goes. So you simply reduce the equation to something like this, plus da 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 plus a1 m plus a0 equals to 0. And this is simply just a polynomial in terms of m, and this is what we call the characteristic equation. This is the characteristic equation, and basically we can use this to find the roots. So we can find the roots for which this function, this polynomial function, is equals to 0. So you get roots m is equals to m1, m2, m3, etc. So there are specific types you can get from a polynomial. You can get two types of roots, right? You can get either real roots or complex roots. And we're going to study both of them. So in the case of a real root, right, basically you just get m1, m2, m3, where all of these are basically real numbers, hence the name real root. So in this case, the solution, or the now yc, which is called the complementary function, is basically like a general function, which is the general solution for a homogeneous equation, right? Yc will be equals to the sum, or the linear sum, of all of the exponentials raised to the mx, raised to the power of a root multiplied by x. So in this case, it will be like m1 c1 x plus c2 m2 c2 e raised to the m2x plus c3 e raised to the m3x, and so on and so forth. And if, for example, you got a repeated root, and that root, let's say root m repeats n times in a polynomial of this type, then the way that you would write the solution for that, or that, like, because yc will be equals to c1 y1 c plus c2 y2 c plus etc, etc, right? Let's ignore this for a second, and let's say y1 describes the function for the root m that repeats n times. So if you want to find that function, it will be y equals to c1 plus c2 x plus c3 x squared plus cn xn minus 1 e to the mx, e to the mx. So this would be the form of the solution for a real root that repeats n times. Now we go to complex roots. So we go to complex roots. A complex root, right, will have the form m is equals to alpha plus beta I. So the solution will be very similar. It will be e alpha plus beta I, right, c. But in this case, there's a property about, especially for complex roots, says that they occur in conjugate pairs. So there would be, if there was a root m is equals to m1 is equals to alpha plus beta I, there exists and must exist another root m2 equals to alpha minus beta I. Now this property comes from where? It comes from the quadratic equation, because minus b over 2a plus or minus 1 over 2a square root b squared minus 4ac. Now this term is negative. This results in a imaginary number. So you can say, you can define, for example, I of the magnitude, square root of the magnitude of b squared minus 4ac over 4a squared, right? So this negative b over 2a is what gives the alpha, and this value over here is what gives for the beta. So there's a plus or minus, so that's why there's always conjugate pairs. They always occur in conjugate pairs. So there's going to be c1 e to the alpha. In this case, let's say c1 prime, because you're going to see y later. It helps us in our calculation. c2 plus alpha beta I, right, multiplied by x, sorry. Of course, here should be minus and x as well. So this is the form of a solution, or the form of a root conjugate complex root pair. Now we can simplify this further. How will we do that? We can get the alpha x out, so we can factor out e to the alpha x, and it becomes c1 prime e to the beta I beta x plus c2 prime e to the negative I beta x, right? And now we can make use of some complex identity that we learned, right? And it is that e raised to the I of some beta will be equals to cosine beta plus I sine beta, and that e to the negative I beta equals to cosine beta minus I sine beta. This is a complex identity that can be proved using the Taylor expansion of e and the Taylor expansion of sine and cosine, right? So in this case we make use of this, but first we make use of it, so it becomes e alpha x c1 prime cosine beta plus c1 prime I sine beta, right, that's 1, plus c2 prime cosine beta plus c2 prime, in this case minus I sine beta. In this case beta x beta x and beta x, right? Because you just substitute beta for beta x, right? And then we sum or like factor out, so we get like the c1 prime plus c2 prime cosine beta x plus I of c1 prime minus c2 prime of sine of beta x, right? So this is one alternate form of the solution that you can write it in this way, or you can simplify it further into something that would look familiar to people who have taken harmonic motion. I'm gonna see that in a second, right? So we define c1 prime plus c2 prime to be a new variable c1, and we define c2 to be defined to be just c1 and the I multiplied by c1 prime minus c2 prime, right? In this case, you get e to the alpha x of c1 cosine beta x plus c2 sine beta x. This is why we place the prime there, so that we can differentiate between them and make something a little bit more nicer. Now, what we're gonna do here is we're gonna do something weird, right? We're gonna define a circle, or sorry, a triangle. I'm gonna define a triangle with c1 is the opposite, c2 is the adjacent, and c1 plus c2 squared squared square root as the hypotenuse, right? So we say that sine, and we define an angle delta such that sine delta will be c1 squared plus c2 squared, and that cosine delta will be equals to c1 squared plus c2 squared, all square root, also the square root over here. And sorry, that's a really bad square root. It should be like this, right? So we can factor out a c1 squared plus c2 squared, and we get e alpha x c1 squared plus c2 squared of, now what becomes c1 squared plus c2 squared square root cosine beta x plus c1 plus c2 squared square root sine beta x. Now we can use these trigonometric stuff, so it becomes e alpha x c1 plus c2 squared square root of sine of this delta cosine beta x plus sine, oh no, it should be cosine delta sine beta x. Now notice that this is like the sum, right? This is basically the sum. Over here, this is just the sum, or this is the sine of the sum of two angles, which is delta plus beta x, right? So now we can write the differential or the solution as e to the alpha x multiplied by c1 plus c2 square root squared, right, multiplied by the sine of delta plus beta x, sine of that, right? And notice this is the solution for a complex root, or the pair of complex roots, right? So notice that this is similar to what, right? You can define this to be a constant, and it becomes c sine of beta x plus delta, which is really similar to, of course, the equation of a harmonic oscillator, right? So in this case, this is c, this is sine, because usually it's an omega x plus delta, right? Sine of omega x plus delta, and then some like amplitude w or a, sorry, this one should be a, this is the amplitude. So this is like very similar, and is much useful form for the solution in like physics applications and harmonic motions and oscillators. So to summarize, you can write the solution of a complex root in any of these methods where gamma, C's, and the C1s and C2s are all constants. Now notice that this one should be C1 prime. This one should also be C1 prime. And in this case, C1 plus C2. And yeah, that's pretty much it. Just remember that in this case, the complementary, this is called, what is it called again? Yeah, it's called the complementary function or the complementary solution, which basically describes the solution of a homogeneous function with constant coefficients with functions in terms of the roots of that characteristic equation. And why this thing comes in handy is because when you have the same thing, so when you have the same thing, but now you have a function q of x, then the solution, the general solution, will be that complementary function. So like, imagine you take this, set it equals to 0, and solve to find the complementary function by finding the individual roots and the individual solutions, plus now a particular solution. And we will study in the next section the particular solution, how to find it by method of basically, what's it called? Yeah, method of undetermined coefficients. This was quite long, and yeah, that's pretty much it.